Good afternoon and good evening to the judges, panelists, fellow participants, and attendees. I am Chirantan Ganguly, and I will be presenting the methods and results of Team CLAN CDAC Localization using AI/ML platform for the problem statement 16 of ITU AI/ML in 5G Challenge, location estimation using RSSI of wireless LAN. We are a team of 4 industry professionals from CDAC and 2 research interns. With the advent of 5G technology, augmented reality, and IoT technology, the need for accurate localization, both in indoor and outdoor scenarios, has increased manifold. GPS has been the leading technology fulfilling our needs of accurate localization. But just like every other technology, there are some shortcomings associated with GPS too. So, although GPS works more or less correctly in outdoor scenarios, in indoor conditions, its accuracy degrades. As in indoor condition, the number of satellites which can be seen from the GPS receiver decreases due to reflection and absorption of the GPS signal from various structures. Mathematical modeling and practical experimentation both show that the attenuation of the GPS signal can reach as high as 2.9 dB per meter of the structure. This results in the signal power levels decreasing to about minus 150 dBW to minus 200 dBW, which is lesser than the typical noise power level of minus 130 dBW at room temperature. This shortcoming of GPS performance has fueled the need for development of location estimation techniques leveraging WLAN parameters and AI/ML algorithms. So why would we use RSSI among all the various other parameters associated with a wireless LAN? So RSSI, or Received Signal Strength Indicator, is a measure of the received signal power. It is 10 times the logarithm or the ratio of power received to a reference power. And as we know, power dissipates from a source as it propagates out, and the relationship between power and distance is that of an inverse square law. Thus, as RSSI is a measure of power, a theoretical relationship exists between RSSI and distance, which is highlighted by the equation shown. If we are able to figure out the distance of a node whose location is not known from a set of points whose location is known, we would be able to locate the unknown point. The RSSI-based technology is especially popular among researchers as it does not require any additional hardware. Although a clear theoretical relationship exists between RSSI and distance, practically it is not the case, as is shown by these two graphs taken from the study reference below. The first image shows a clear relationship between RSSI and distance when the values were taken from an access point facing north. However, the second image shows the RSSI value measured by the same access point when measuring from the east direction. This highlights the sensitivity of RSSI to the environment and the sudden variation in it due to the effects such as multipath fearing. This highlights the problem in establishing a clear relationship between RSSI and distance in a practical scenario, therefore reducing the reliability of such a model. Another problem with RSSI is that human bodies shadow Wi-Fi signals to a great level, as human body is made up of 70% water. So that causes a variation in RSSI values when humans are present in a room where the localization is taking place. This has been illustrated by these two images. The RSSI value changes abruptly when a human is present in the room, but it stays more or less stable when a human is not present in a room. So now we discuss some of the localization procedures which can be used with RSSI. So the first one, which is very popularly used, is called multilateration. So in multilateration technique, we have a set of access points, typically more than 3, whose locations are known. Let's say xi, yi. In this scenario, we also know the value of the RSSI for the reference points with respect to each AP. Using the relationship between RSSI and distance, we can calculate the distance between the reference point and the access point. And with the distance known, we can use multilateration technique to locate these reference points. So the equation here illustrates the relationship between distance and RSSI. Here, the parameters n is the path loss index, which is dependent on the medium in which the localization is taking place and the environment in which it is taking place. And a bar is the average RSSI value measured 1 meter away from the AP. Both these parameters have to be found out by experimentation. So the distance can be figured out from the RSSI. Now, when the distance has been figured out, we can form these equations using the Euclidean distance formula. Here, the only unknown variables are x and y, which is the location of the reference point. xi, yi is known, which is the location of the access points, and di is the distance which we calculated from the RSSI. So upon solving this set of equations, we will be able to locate the reference point. So this is one of the methods of how we can undertake localization. Another technique frequently used for localization is RSSI fingerprinting, which we will discuss now in brief. So unlike multilateration, the RSSI fingerprinting does not bother about the relationship between RSSI and distance. Instead, it analyzes the distribution of the RSSI from data points in the localization area to be used in training. And it uses algorithms such as k nearest neighbor for locating the validation or test points. This procedure has been illustrated in this diagram, where the red points are the training points and the blue points are the testing points. One precondition exists, however, for using RSSI fingerprinting technique, which is the training data set must be robust with training points uniformly spread throughout the area in which the localization has to be done. Although RSSI fingerprinting technique typically gives better accuracy than multilateration, it is very much environment sensitive and requires a thorough training phase. Smallest changes in the environment, such as putting an additional chair in a room where the localization is being done using RSSI fingerprinting, can lead the model to give erroneous results. Also, any localization scheme using fingerprinting technique has to be recalibrated every time before using in a new environment, which is an inconvenience. So these were the various localization techniques. Now let us look into the data set which was provided as a part of this challenge. The data set provided consists of information of 4 access points, such as its location in terms of latitude and longitude and its environmental specifications. There are, however, only 13 reference points whose information was given for the training of the model, and 13 other reference points were present for validation. The information provided for each reference point included its local location, the RSSI values in dBm measured with a timestamp and a channel number. There are 4 APs and 13 RP in both training and testing datasets, and 100 observation of each RP was taken from each AP. So that is 13 times 4 times 100, that is 5,200 rows of data were given in both the training and the testing dataset. So here, the area where the experiment was conducted has been shown. The APs are present at the vertices of a 35 by 15 meter rectangular plot. The graph here shows the various points in the dataset. The red points indicate the access point, and the blue ones indicate the training point. The green points show the location of the testing points. As can be seen from this plot, there are not many reference points not many reference points as required for accurate fingerprinting, which we discussed earlier, as the reference points are not uniformly spread throughout the area where the localization is happening. So what is unique about this problem and what is challenging about it? The data set which has been provided with the problem statement is not as robust as it should be to match the complexity of localization. The reference points have been observed from each AP for a period of not more than 100 seconds, and one sample was taken per second. Only 13 reference points were present for training, and this is a low number of RPs, which will severely limit the performance of any RSSI fingerprinting model. Also, the RSSI values measured from the RP to all the APs were more or less synchronous. The following data restructuring steps were followed before the application of the machine learning model. Firstly, we restructured the data and included the important features of both the AP and the RP, which would be required for training our models. As we previously saw, the RSSI values are prone to sudden changes, and therefore a data smoothing process had to be undertaken to reduce these sudden changes in the variation in RSSI, which would hamper the model performance. We employed moving averages of the RSSI values to smoothen the data set. This has been shown in the image where the blue line indicates the original RSSI value and the yellow line indicates the smoothened data. We also removed some of the outlying RSSI values which could hamper the model's performance. Here are the proposed model for the localization using RSSI. We experimented two methods. One is to estimate the distance of the reference point to the access point using RSSI, and thereafter to do multilateration to find the location of the reference point. The second method is based off the concept of RSSI fingerprinting, where we directly estimate the location of the reference point from the distribution of RSSI in the localization area. The machine learning models which we used for implementing these models were linear regression with polynomial features of degree 2, k nearest neighbor, and EDA boost regression. So, as we have mentioned, RSSI follows an inverse square law with respect to distance. That is, RSSI value is inversely proportional to the distance squared. Therefore, to estimate the distance using a machine learning algorithm, we used the linear regression with a polynomial features of degree 2. For undertaking the fingerprinting experiment, however, we used the k nearest neighbor regression. Meanwhile, ADA boosting was used to get improved results from regression using its ensemble approach. So now let us discuss the performance of various models and what were the results obtained. So these were the metrics that were used by us for evaluating the performance of the model. The mean distance error and the max distance error of localization are the metrics whose value, the lower it is, the better is the performance of the model. And the percentage of data yielded which yielded a distance error less than 2 meters is a parameter whose higher value indicates a better result. So to have a reference model for our machine learning model's performance, we created a baseline model using the mathematical relationship we have previously shown. The errors obtained using baseline models have been shown in this slide. We can also see the results obtained in the Japan round of evaluation using the baseline model. The plots show how the predicted value is following the original value. The graph from the Japan round of evaluation is more crowded than the final round, as more number of reference points were present in the Japan round of dataset. So these are the results which we obtained for linear regression with polynomial features of degree 2, which is the graphs are also illustrated in this slide along with the results. These were the results which we obtained following the fingerprinting approach using k nearest neighbor with k equals to 3. We notice a reduce of accuracy of the K nearest neighbor model in the final round in comparison to Japan round, as more number of reference points are provided in the Japan round, that is 26. However, in the final round, we only had 13 reference points. So this slide illustrates the results obtained from the AWS regression along with the plots. So in this slide, we present a tabular chart which shows the error of the different models resulted in the final as well as in the Japan round of evaluation using multilateration method. And the computational complexity can be understood by the latency of these models. This table is illustrating the performance of the various machine learning algorithms using the fingerprinting method. AdaBoost algorithm using fingerprinting method has yielded the best result on the data which was provided, with 23.27% of the data predicted with less than 2 meters of error. As a summary, we can say that in this project, we applied machine learning approaches and algorithms to estimate the distance and hence the location from the RSSI values. These models were able to map the relationship between RSSI values and the distance from reference point to access point and hence conduct localization with a certain degree of error. Of the various algorithms which we tested and tried, we can say AdaBoost Regression outperformed others in its accuracy, yielding the best result. For future research and model building, an enhanced dataset with more number of reference points spread throughout the localization area would be helpful. Although we use more moving averages for smoothing the data, Kalman regression and Kalman and Gaussian filters can be considered to handle the fluctuations in the RSSI value. Moreover, using wireless LAN parameters such as link quality index, time of arrival, and angle of arrival, along with RSSI values, will fetch better and more robust results, as these parameters are not that much affected by the environment around it as RSSI is. So these were the references which we used to conduct and complete this study. And thank you all for your attention. It was a great pleasure presenting our work in this grand finale. Thank you.